Hey everybody, we're just doing a quick mic check or audio check, so you can hear me. Just type a quick question from the audience so I can verify. We'll go ahead and wait a few minutes to get started to give people a chance to log in. So just a quick check to make sure you can hear me. All right, cool. Thanks for the validation that I'm being heard. Again, just have a presentation or an announcement saying that we're going to give everyone till about 5 after, so another 3 minutes just to give people a chance to log in, and so I'll be on mute until then. All right, it's just about 5 after. The viewership seems to have stabilized quite a bit, so I'll go ahead and get started. My name is Doug Otis, lead mechanical engineer at PADT, and this is the presentation going over the updates to additive manufacturing and topology optimization in ANSYS 2020 R1. So for those of you not aware who PADT is, what we do, quick little summary. So founded in 1994 by 4 turbo engineers based in Tempe, Arizona, with offices in California, Colorado, New Mexico, Utah, and staff in Texas. Approximately 85 employees, kind of spread across business units ranging from numerical simulation, 3D printing, and product development. So operating on the sales support and providing services in all three of those industries. So I am on the numerical simulation side of things. So on that side of the house, we are an ANSYS Elite channel partner. We're also a reseller of Flownex and also provide HPC compute solutions for large complicated models. We provide frontline technical support to all of our customers in the Southwest U.S., ranging from California to Texas. We provide training and mentoring pretty much to anyone who asks and our schedule works out for. We also have a services department doing numerical simulation, both as overflow and providing expertise in physics ranging from static, structural dynamics, fluid dynamics, electromagnetics, and coupling all those fun physics together. Again, we're kind of operate in the Southwest U.S., ranging from California to Texas. An award-winning technical support provider, very strong technically, customer-focused, and really a lot of long-term relationships with large customers and small customers alike, providing a strong relationship and strong return on investment for the software. So this slide needs to be updated. We're no longer introducing ANSYS Cloud. It's been out for quite a bit now. So if you're not aware, ANSYS has a cloud offering that utilizes the Microsoft Azure network. And it really offers a really pretty seamless transition to cloud computing. So rather than you having to maintain IT staff and hardware locally, you can burst to the cloud, and it's as easily as essentially clicking a button and logging in one time. So again, it's as easy as HPC should be. You don't have to worry about maintaining any type of interconnects, any type of installation control, anything like that. So if you're curious at trying that, contact our sales staff. There's, I believe, still free 30-day evaluation trials. Contact us at info@pdt.com or phone number. Obviously, if you're outside of our sales territory, you can also contact your support provider for additional information. So we'll talk about topology optimization right off the bat, and so both level set and density based. And so for both of those workflows, there is a new design validation process. So previously, you would have to go through, generate your optimized shape based off of your inputs, regardless of if you're running level set or density based. You would then export out or link that result set of your topology optimization to a downstream geometry session in SpaceClaim. You then go through and run whatever type of reverse engineering or cleanup, shrink wrap, smoothing operation you want, and then you link that into a however many simulations that you used prior to generate that optimized shape to actually look at stresses and strains, deflections on that optimized part. So now it's a lot more automated. So you can just right mouse click, say to transfer to design validation system on your topology optimization result. It automatically builds all of your input physics. So if you had two structurals, a modal, something else that were feeding that top opt run, it automatically builds all of that for you. And the big thing here is it automatically rescopes all of your boundary conditions for you. So the thing to note here is that in order for this automated process to work, you have to do one thing up front. And so it's the exact same process regardless of if you're running density or level set. You define your analysis, you run your topology optimization. After it's done, the picture in the bottom right-hand corner on your topological element density plot, you right mouse click on that and you insert a smoothing object, and then you specify on it that you want to export the model. It's very important. If you don't do that up front, then the automated rescoping, recreation of everything for you doesn't quite work. So do this up front. You don't have to insert this before you run your topology optimization. This is just before you do that design validation. Right mouse click, insert it, set the export to be yes, and then you can go ahead and run your validation study. So some additional constraints that were added is the reaction force constraint. And so you should be able to specify a range of values. So just an additional constraint for both topology optimization engines for both level set and density based. So it offers some pretty interesting effects on being able to essentially tune the reaction force based off of what's important versus not important in your model. So you can see that without a reaction force constraint on the two clamped faces on the left and the right side, you can see that we essentially just disconnect those two faces from where the load is occurring to where it's being reacted out. And so if you need to fine tune or limit the force going through certain areas, this is a nice control or criteria that you can insert to your topology optimization simulation. User-defined criterias, these were beta at the last rev, and these are essentially just ways where you can tag nodes, tag vertices, tag finite element objects, and essentially create your own constraints or objectives. So if you want to make sure that as I'm removing mass from one section, I want to make sure that the deflection at a node at another location meets a certain criteria or to drive an objective, then this allows you to do that. So these are inserted in the simulations that feed into your topology optimization. So if you look at the picture on the left, you'll see that these are criteria that are inserted in the static structural, the modal, what have you. And so these are primary criteria are essentially just a tag value of looking at displacement in a particular direction. You can then create composite criteria, which essentially allow you to define a worksheet where you can add, subtract, do whatever you want between relative primary criteria. And so if you're trying to look at, I want to make sure that the total distance between these two nodes is a certain value, you can work your way through creating a worksheet that drives that type of equation, that type of relationship. And then in your topology optimization, you can specify that your criteria are these primary or composite criteria downstream. So specifically on the Levelset topology optimization, we'll go over some modifications. And so the big one is just the way that we handle in a multi-objective scenario, whether or not we're using kind of the standardized summation in order to kind of drive where material gets removed from, or normalized. And so depending on the magnitudes of the loads that you have, it may make sense to use the standard or the normalized. It's just another option for how we treat a multi-objective criteria or a multi-objective topology optimization. So most of these we've already talked about. The reaction force, the ability to specify a limit. User-defined function, it's a kind of a misnomer. It's not a user-defined function, it's user-defined criteria, both primary and composite criteria. And so that's available for both of those. There's been some improvements to how an overhang manufacturing constraint is handled. There's less disk space required in order to perform a topology optimization run, always a good thing. Different way to formulate a standard versus normalized response for a level set. And then there's been some additions or improvements on the Discovery Live side of the house. And so that was, we'll go over that right here. So Discovery Live has supported topology optimization for a bit, but it was limited in what it could do. And so you have the ability to specify multiple analysis environments feeding into that optimization run. There's some additional manufacturing constraints specifically on kind of the max thickness and also a pull direction to help prevent some internal cavities essentially forming or hollowing out in a particular direction. So if you're looking at creating something specifically for a molding or a casting application, it's a good use. So as far as changes specifically to the density-based solver, we'll get into a few of these. So this is actually new to me. I didn't realize that you could do bolt pretension in a topology optimization run, so a little ignorance on my part. But the previous limitation was that it had to be in the load position. So bolt pretensions operate in a load lock adjustment and open case. So previously, if you wanted to include a bolt pretension effect as part of the driving load that you're optimizing for, it had to be left in the load position. So that's been removed. You can now specify a lock condition for your topology optimization run on with the density-based solver. There's been a less restrictive mesh rejection algorithm for specifying an extrusion manufacturing constraint, and so basically not being as strict as we previously were, which may have erroneously rejected some output mesh shapes. So previously at 2019 R3, there were some additional constraints that were available specifically on mass and inertia information, but it was only available on the level set. So it's been released to the density-based solver in beta at 2020 R1. And so it allows you to specify what the center of gravity is and where it's located on a particular axis. So pretty much rolling over functionality from level set to the density based. So again, that's going to be both the CG and the moment of inertia. So it's very useful for if you're trying to replace a part but not change the overall dynamic behavior. So making sure that natural frequency wise and also from an excitation or any type of dynamic response, if you're trying to essentially do a one-to-one replacement on a CG and moments of inertia for a launch vehicle or anything like that, you have the ability to insert these criteria. Constraints. There's a new advanced filter that's available. It's a beta feature, so on the project schematic, you have to go and turn on beta features and specifically choose this. And it's essentially just, rather than using a linear filter to decide whether or not elements are on or off from a density application, we're using a nonlinear filter to kind of create some more elegant or better defined shapes. So you can play around with it, see if that gives you a more robust or interesting design. So new at 2020 R1, this isn't topology optimization, this is shape optimization. So topology optimization, you can think of, I have this box, I don't know what it needs to look like in order to transmit a particular load to a particular reaction or a particular constraint. So shape optimization is where I'm going to be distorting the mesh based off of whatever criteria, whatever objectives that I define. So this is beta, and usually, we typically don't go over a whole lot of beta options in release presentations, but this is a pretty cool new tool. So making sure that people are aware of it. And so, there wasn't shape optimization for a while in ANSYS, and so making sure that people are aware of it, people can start playing with it and see if it works for them. So as far as the capabilities, it's a new feature, it's a beta feature, and so as far as the different constraints, the different loading environments, the different objectives that it supports, it's going to be limited, but for the most part, for a static analysis and a modal analysis, it offers some interesting utilities. So here's an example of a bowl. So we have, rather than starting out with a domain and then whittling out elements based off of a pseudo density or a level set way of handling a closed loop, we are instead distorting the mesh based off of the criteria that we define. And so it is distorting the mesh, and so some limitations here is it only works on TEP meshes right now. And so, but the nice thing here is you get a smooth shape out of the solution, and you can also view stresses, strains, deflections, all those post-processing results directly on the distorted mesh. And so on the topology optimization side, we're essentially kind of whittling away elements, and then there's a validation check in order to actually investigate what those stresses and strains are. Here you can actually view those results on the actual mesh. So as far as the two comparing, contrasting the two methods, and so one of the common questions I get with topology optimization is, what if the domain changes, or let's say I want to, I have a larger kind of bounding box that defines what my structure can be. And so, the topology optimization, you're essentially limited to whatever bodies you've scoped it to, because that's where we can remove material. As far as the node-based optimization, that we're essentially distorting the mesh in order to meet whatever requirements that we specified. So again, this is a beta option. You can turn it on, play around with it, and a pretty cool utility depending on your application. All right, so that's all on the topology optimization side of things. We'll talk about additive manufacturing. Yeah. So as far as additive prep, for those that can't quite keep all the different naming conventions that ANSYS has for all the additive tools, additive prep is a utility that sits within SpaceClaim. It allows you, previously it was just used to kind of identify what orientation I should use in order to help control against distortion, build time, and the amount of support I would need. It's since grown with some recent additions of other tools to essentially be able to build an actual build file for a machine. And so each row we get a few more utilities as far as controlling machine-specific parameters. And so specifically here, you can add some tree supports. Those are a new support structure. At 2020 R1, the ability to write build files for SLM and also generate CLI files for EOS machines. You can modify power, speed, and focus parameters for different vector scanning types. You can modify the scan order, so depending on if you want to do hatch, then border, or whatever sequencing you want to do. There's built-in cost estimators, so that's an additional output. You can kind of see, how expensive something can be based off of an orientation, and make decisions on your overall build process. So next on the ANSYS additive side of things, with the specifically the print and sign. So this is the formerly known as 3D Sim. It's been in the ANSYS orbit for quite a while, for the past since at least version 19, if my memory's going back correctly. And so this is essentially a machine kind of specific, so it's a nice utility. This is not running in the ANSYS mechanical interface. You essentially import an STL file, specify some materials, and then there's a series, essentially 3 levels of simulation fidelity that you can run through in order to capture how your part builds, where stresses where potential problems can occur, look for any type of blade recoder impacts, anything like that. So as far as what's new in 2020 R1, the ability, at least in beta, to read EOS build files. There's a new material, the aluminum silicon 10 magnesium, for all the simulation types, so microstructure, just basic thermal history and stuff like that. We can control the laser beam diameter, some additional, or at least some cleanup on the log file to help kind of assist any type of errors or anything like that. The J2 plasticity has essentially been removed from beta state and been improved, or certified. I think that's the word I'm looking for there. The build size was previously limited to, I believe it was like 500 to 600 millimeters on an edge or in each direction. That's been increased to 1 meter cubed. Disabled the support optimization that was originally kind of a standard functionality to optimize the support structure based off of physics, and so that's been disabled, so you don't have to run that each time. There's been a melt pool reference width that's typically used on the additive science thing, looking at, you'd have to dig into the documentation. Long story short, it deals with predicting porosity and density in subsequent layers, or layers below your active layer. And then there's been a new workflow that deals with taking the output from additive print and going into Workbench Additive. So in additive print, additive science, we're solving a voxelized state, and there aren't a whole lot of advanced creep models or progressive cutoff functionalities available. And so those have been, there's a workflow now of taking your as-built condition, mapping that over and running that within mechanical and adding some additional simulation capabilities. So on the Workbench Additive side of things, so Workbench Additive is not additive print, additive science. This is running ANSYS mechanical. So Workbench Additive is essentially a linked thermal analysis to a static structural analysis. It is wizard driven to walk you through all of the process to essentially specify some machine parameters, some boundary conditions, and other stuff like that. And so new in Workbench Additive is the inherent strain method. And so that's essentially kind of a port of one of the solver types within additive print. So the inherent strain doesn't actually solve a thermal environment. Instead, we use the melt temperature as essentially a guide to essentially on a layer by layer basis turn on elements at a particular pre-strain, and then we essentially capture how the model stresses or distorts as we build up layer by layer. And so this inherent strain method offers a stress scaling factor. That's what SSF, strain scaling factor. They're related. It's stress or strain. I can't remember off the top of my head. But this allows you to run some calibration prints on your machine in-house and then essentially account for those machine-specific behaviors in your model. So that way you can print a few different shapes, take some measurements, figure out what the actual scaling factors are versus a assumed kind of idealized numerical simulation, apply those factors, and now you can kind of fine-tune your simulation for a specific machine. Some additional additions to Workbench Additive is the AM Connect macro. So this allows us to connect a layered TET to a voxelized support. We'll get into that in a couple slides. The wizard has been updated to expose the inherent strain, preload some materials, and also support a sequential progression for a cutoff operation. We'll get into that in later ones. There's the print to Workbench, so additive print to Workbench to simulate the cutoff, smaller result file size, and then some additional improvements to the blade interference and conformal meshing for voxelized parts and supports. All right, perfect. So talking about Workbench Additive, so I kind of talked about this already, the inherent strain method. So rather, the default way that Workbench Additive operates is we're solving a transient thermal, solving for how the temperature gets distributed over time through the build process. And then we map that over to a static structural. Inherent strain instead just runs through the static structural with kind of the melt temperature based applied strain. So these can be isotropic or orthotropic, depending on if you want to account for essentially kind of the print scanned orientation. And really it's I call it almost a straight port of the functionality. It's not the exact same solver, but it's adding the same functionality that was in additive print is now in Workbench. So STLs that are generated from additive print. So remember, additive prep. Even I confuse the words apparently. So STL supports generated from additive prep can be represented as Cartesian meshes. And so all you'd have to do is import an STL support within mechanical. It then creates a voxelized mesh based off of how much material is in each voxel. It will calculate the appropriate knockdown factors. So these voxelized supports, when we're going through and tying it to non-uniform shapes, and if we're using a layered TET, there's a command snippet that you have to use in order to properly connect these dissimilar meshes. By default, they're not shared nodes. So this is essentially, if you're an APDL user, to me, it's kind of like a CE grid command in order to tie together the degrees of freedom between dissimilar parts. So you have to use the AM Connect and then use the part ID for your actual printed part. That's your material ID. And then support ID is the material ID of your voxelized supports, and it automatically generates the constraint equations to tie those together. So you'd have to insert this on both the thermal environment and the static structural environment in order to properly tie together those thermal and structural degrees of freedom. So there's also a beta support in order to essentially have the part and support meshed with a voxel and handle that kind of shared node interface. Rather than using a layered set, if you want to use a voxelizer, the Cartesian mesher to mesh your part, this is the way to do it. It's a beta feature, as a beta feature. All right, so I had briefly mentioned taking additive print. So that is outside of mechanical. That's where you essentially just, it's a web-based kind of interface. You import an STL file, specify some machine settings and hit solve, and then post-process using, I forget the name of the tool off the top of my head. We can now take that as printed, or the predicted shape or distortion of our part from additive print, and then continue our simulation within our static structural simulation. And so this gives us some kind of elegant heat treatment cycles. So if you're trying to account for any type of heat treatment to your printed part, there are some very simplified ways that where you essentially just zero out the thermal strains and see what that does to your part. Or if you want, or if you know what type of creep material model you want to use in order to capture any type of relaxation, you would have to go into mechanical. So this workflow allows you to go from additive print to mechanical and add some additional material functionality, and also do a progressive cutoff. So hopefully the animation is going to work. Oh, so this, again, the wizard has been updated in order to essentially allow us to specify a cut direction, so we can see as we go through and we remove our part from our build plate, what does that do to the overall finalized shape and pre-stress to our part. So yeah, pretty cool. So as far as additional enhancements and corrections, so file size always seems to be an issue. People run bigger models, so there's a lot more resources involved. So the result file size has been optimized, so only output quantities for additive. And so always a good thing using less disk space. So for STL supports, scope to an STL file, that file is now maintained in the Workbench project. Restarts are supported for user steps and the inherent strain method. There's scaling factors in the thermomechanical build simulation in order to reduce or increase the obtained distortion. So if you're trying to kind of calibrate or optimize or back out of and predict a distorted shape, you can play around with the stress scaling factors to see essentially how you need to distort your input STL. We can use block supports and automatically calculate the knockdown factors for thermal density for more realistic heat dissipations. And on the first layer of the build, on the structural side of things, the T-melt isn't applied. So there have been prior cases where there were super high distortions on that first build layer on the build plate due to some kind of temperature, excessive temperature loading. And so that's been removed. So it eliminates some spurious hot spots on the build plate and excessive plate deformation. All right, so I didn't say anything up front. So at the end of this, you'll get a copy of the PDF version of this. I apologize for not kind of doing the standard housekeeping. But yeah, everyone gets a PDF of the slides after this. There's always a slight lag between when I say type your questions and the question from audience and when they start popping up. So I'll go ahead and wait some time in order for some questions to start coming in. Otherwise, if you don't have any questions, thank you for attending. But like I said, I'm not closing the meeting. I'm just going to start waiting, and I'll mute myself until questions start popping up. All right, so one question, kind of in the optimization family, not necessarily topology or shape. Question about, does ANSYS have any tools for optimizing carbon fiber composites? So that can be done using ACP. So in ACP, you can play around with different orientations, different layup schedules, and that kind of stuff. And so the answer is yes, but it would utilize Design Explorer or just a parameter manager and ACP. And so the overall process of that would be you essentially have a shell surface or a surface body that you import into ACP. You run through and build up your layup, and then you have the option to either extrude that as a solid or keep it as a shell depending on the thickness of the composite. You can parameterize certain inputs, then you would pass that a layup over into mechanical, run through that simulation and tag whatever outputs you want to post-process. ACP post-processing there's quite a bit that you can do with the mechanical now. And so the answer is yes, it's just not using any of the tools that I really discussed today. It's a mechanical and an ACP and parameter manager or Design Explorer. All right, so next question, do topology optimization and shape optimization require any additional licensing? And so no. You should have the ability to do any type of topology optimization. I think in most ANSYS environments, I'd have to double check. Some of the, I do know that if you're looking at doing lattice optimization, you have to have some additional licensing there, but most of the topology optimization that we've gone through shouldn't require an additional license outside of what you're using to run mechanical. All right, a question about currently it takes a lot of time for smoothing and remeshing of optimized objects. With the new workflow, will the new workflow reduce this time? Maybe. It really depends on how complicated the shape is. And so, I had mentioned that the new workflow essentially smooths it and sets up all your boundary conditions, all of your analysis environments. But usually where people have a hard time is on the validation is generating the mesh there. And so right now, pretty much the standard workflow is you have to insert a patch independent mesher to TEP mesh it and handle kind of, we're essentially treating that as dirty CAD, which the independent mesher is really good at dealing with. And so the smoothing, it really just is like a quick smoothing operation. I forget the controls that are available on that smooth option. I think it's a node move percentage. But you still have the ability, if you don't like essentially the output from this automated method, you can still push your STL into a space claim session, use all of the shrink wrap, the smooth, whatever your favorite reverse engineering tools are there, that workflow is still available. And so as far as cleaning up dirty geometry, really this new method takes that out of the equation. And so really it comes down to, if you don't like the output smooth shape, then you are essentially still in the same workflow. Hopefully that answered that question. Do you have any top op tutorials for this release? That's a great question. I don't know. I think the only tutorials I can think of right now is, so if you launch, if you're using Discovery Live, there are some pre-built templates that walk you through a bracket optimization. As far as what's available on the mechanical side, I haven't seen anything, but at the same time, I haven't looked extremely hard. I usually just make a simple block, simple bracket, and play around with it. So if you're having trouble finding anything, and more than happy to help. So if you're in our area, so email the info at all that stuff. All right. Okay, so I'm going to skip one question. I'll come back to it. So given your experience, do you think Levelset is better than density-based? Oh man, that's a tricky one. So I think Levelset has a lot of very promising functionality. I really like, you get a nice clean shape out of it. in my experience, it seems that it can be a little slower. It seems like it's gotten faster lately. And really, between the two, there's, when Levelset was first introduced, it was pretty limited in some of the manufacturing constraints versus the density-based. But my personal opinion is I like what Levelset does as far as it seems to kind of provide some more elegant shapes. But I almost feel like an art critic with this, and so I think they can both give you what you're looking for, depending on the constraints that you're applying. But put me in the Levelset camp. I think it's a pretty cool tool. Question about, can you include ribs with novel cross sections with carbon fiber composites? It's not directly related, where it's got optimization in it, maybe. The answer is yes. I don't quite know what we're talking about as far as if the ribs are composite, if we're essentially connecting a solid to, adding some additional support to a composite. There's a lot of things that we can do with composites, and so as far as what's possible, the answer is typically going to be yes, but it really depends on the level of detail that you want to go into, and if if a rib is a composite or just a solid that's attached or riveted somehow, it's different workflows in order to properly assemble a mesh. So I'm going to answer yes with a but, because we don't know specifics, but most things, it should be doable. Obviously, we don't know the specifics, so have to talk more. All right. Well, I think I've either talked around most of these questions or actually answered them, and so I haven't seen any more come in. Again, I'll leave this open for a few more minutes. I'm not closing it. I'm just muting myself until more questions come in. Ribs are composite, but it's that thickness. You should be able to import multiple surface bodies in order to define how the composite's actually shaped. But what I'm thinking of rib in my head versus what you're actually looking at on your computer may be completely different. So, it's a good topic offline. All right, again, I'm just going to mute myself. If there are any more questions, please type them in. I'll do my best to handle them. Again, otherwise, that's the last slide I got. Thank you for attending, and everyone gets a PDF as a party favor. That was my first not question. No problem. Happy to do this. So yeah, I'll go ahead and leave this open for another 2 minutes on my watch, and then I'll go ahead and close it. Thank you for attending. All right, that was 2 minutes on my clock. So go ahead and end the presentation. Thanks for attending. Hope everyone has a good one.